In this lecture, I will discuss the strong and weak topologies in the space of bounded linear operators from X and Y. So we have fixed once forever two Banach space, X and Y. Remember that we represent by Lxy the class, the linear space of bounded linear operators from X to Y. They will be represented by M. And I want to discuss topologies, so I will introduce three topologies. So the first one, it's called the uniform topology. The uniform topology is the one associated to the norm in which we defined in Lxy. So remember, if M it's an element of Lxy, we defined a norm of M, which is the supremum over all points x in X with norm equal to 1 of Mx. We have shown that this is a norm. This norm induces a distance in this linear space, and the uniform topology is the topology associated to this distance. This is one topology. The second topology, which is called the strong topology, is defined as follows. Well, you consider for all x in X, let me represent by gamma x a map from Lxy to Y, which associate to a bounded linear operator M the point in Y given by Mx. So this defines linear functions on Lxy. The strong topology is the weakest topology which makes these functions continuous. So the strong topology is defined as, this is topology for which for all x, gamma x is continuous, and it's also the weakest topology with this property. So the strong topology is the weakest topology which makes these functions continuous as functions from this space to the space Y. So this is a strong topology, and finally we have the weak topology. And for the weak topology, instead of taking these functions, now I will fix x in X, L in Y prime, and I will define a functional gamma xl from M to our scalar set, which we called K. And this is, to each M, we will associate the value mxl. So recalling the notation, this means that this is an element of Y, this is an element of Y prime, and we are applying to Mx the bounded linear functional L. And so the weak topology is a topology which makes these functions continuous. So it's characterized by two properties. Under the weak topology, these functions gamma xl are continuous. And it's the weakest topology with this property. And so in this lecture, we will investigate some properties of the strong and weak topologies. So we introduced the notion of topologies, uniform, strong, and weak. We have also a definition or a terminology of which is also very important, which is sequential topology. So we'll say that a sequence Mn of bounded linear operators from X to Y, we will say that Mn strongly converge if for all x in X, Mnx converges strongly. So I'm introducing a new definition, a new terminology. So if I have a sequence of bounded linear operators, Mn, I would say that this sequence strongly converge if for any point x, the sequence of points in Y, Mnx, converge strongly, which means that if Mnx converge to some point Y in the topology of Y, which means in the norm of Y. And let me prove immediately a lemma. The lemma reads as follows. So I will never repeat the fact that I have Banach spaces x and y and that I have these bounded linear operators. So let's assume that the sequence Mn n strongly converge. Which means that for all x in X, the sequence Mnx converge to a point in Y. Then there exists a bounded linear operator from X to Y such that for all x in X, M and X converge to Mx. So if we know that the sequence strongly converge, we can prove that there exists a bounded linear operator with the following property, is that for all x in X, M and X converge to Mx. So here's the lemma I wanted to prove. We have a sequence Mn of bounded linear operators from X to Y, and we assume that for all x, mu Mnx converges. And we want to prove that there exists a bounded linear operator M such that Mn converge to M strongly. And the proof is as follows. So let me represent by Ax the limit of Mnx. So let me call Ax the limit of Mnx. And I claim first that A, so now A it's a function from X to Y. For each x, Ax it's an element of Y, that A is linear. And this is very easy, and I leave it to you to prove that A it's linear. So that Ax plus Y is equal to Ax plus Ay. What is more delicate is to show that A it's bounded. So I want to prove that there exists a finite constant C0 such that the norm of Ax is bounded by C0 times the norm of X. And to prove that, let me define a continuous function. I'll prove it's continuous, Fn from X to the real numbers. So Fn of X would be equal to the norm of Mn X. And I will prove that Fn, what I claim is that Fn it's subadditive that it's positive homogeneous and that it's continuous. So let me prove that here. So let me recall that subadditive means that f n x plus y, it's bounded by fn x plus fn y. And this is clear from the definition because fn x plus y is the norm of mn x plus y. But this, by linearity of mn, and then by the triangle inequality, it's less or equal than the norm of mnx plus the norm of mny. And this is fnx and fny. So that proves that fn is subadditive. Then let me show that it's positive homogeneous. So let me recall that positive homogeneous means that fn alpha x, it's equal to the absolute value of alpha times fn x for all scalar alpha and x in x. But again, by definition, fn alpha x is the norm of mn alpha x. By linearity of mn, this is alpha mn x. By the property of the norm, so this is the absolute value of alpha times the norm of mnx, and this is exactly the absolute value of alpha times fnx. So this proves that fn is positive homogeneous. And finally, let's prove that fn is continuous. Now, if we have a sequence xk converging to x, we have to prove that fn xk converge to fnx. Fn xk, it's equal to the norm of mn xk. But since mn is a bounded operator and xk converge to x, since it's bounded, it's continuous, xk converge to x, so mn xk converge to mnx, and therefore the norm of mn xk converge to mnx, and this is fn of x. So we have proved that the function fn defined by the norm of mnx, it's subadditive, positive homogeneous, and continuous. Now, we fix x, and what I claim is that the supremum over n of mn x, that this is bounded by a constant which depends on x. And this is clear because, well, the sequence mnx, it's converging to ax. This means that the norm of this sequence, it's bounded, and this is exactly what we are saying here, is that, well, for each fixed x, the norm of this sequence is bounded by a constant which may depend on x. So now, well, this is telling us that for all x, there exists a constant which depends on x, such that fn x, which is positive, so I can put the absolute value inside, it's bounded by a constant times x, by a constant which depends on x, sorry. Now we have proved, using the principle of uniform boundedness, that if we have such a sequence of functions which are subadditive, positive, homogeneous, and continuous, and such that for each x there exists a constant which depends on x, such that fnx, the supremum in n of fnx, it's bounded by this constant, then there exists a constant C0, finite constant, such that fnx, it's bounded by this constant C0 times the norm of x. So this is a theorem which we proved in the previous lecture, saying that, well, if we have a sequence of functions satisfying these three conditions and bounded pointwise, so that for each x, the supremum, it's bounded, then we can find a finite constant C0 such that fnx, it's bounded by C0 times the norm of x for all n. Well, but then we can use that to say that the norm of ax is the limit of m and x. So the norm of ax is the limit of the norms of m and x. And fnx, this is by definition the norm of m and x. So the norm of m and x, it's bounded by a constant times the norm of x. So this limit, it's also bounded by this constant C0 times the norm of x. And this proves that the linear operator A, it's bounded. So by defining Ax as the limit of m and x, we defined an operator A, which is linear, and now we just proved that it's bounded. So A, it's an element of Lxy, because it's linear and it's bounded. And I claim that Mn converges strongly to A. And to prove that Mn converge strongly to A, we have to show that Mnx converge to Ax for all x, but this is part of the assumptions because we define Ax as this limit. So this completes the proof because we showed that A is a bounded linear operator and that Mn converge strongly to A because for all x, Mnx converge to Ax. Now let me introduce a new terminology. I would say that a sequence Mn of bounded linear operators from x to y converge weakly to a bounded linear operator M if for all x in X, M and X converge weakly to Mx. So the sequence Mn will be said to converge weakly to M if for all x in X, M and X converge weakly to Mx. And I want to prove a similar result by replacing strong convergence to weak convergence. So the lemma now reads as follows. Assume that you have sequence Mn of bounded linear operators from x to y, and assume that for all x, Mnx converge weakly. Then we can prove that there exists a bounded linear operator M such that Mn converge to M weakly. And so let's prove this lemma. So let's assume that for all x, M and x converge weakly. And again, let me call Ax the weak limit. So this is the weak limit of the sequence M and x. First, I claim that A is linear. And this is very easy to prove. So I leave to you to check that A, defined in this way, is linear. So now what we have to show is that this linear operator from x to y, it's bounded. Well, so we have a sequence here, m and x. So fix x in x, and consider the sequence m and x. This sequence is converging weakly to an element of y, which we are calling ax. We have seen, when we studied weak convergence, that this means that this sequence is bounded, and that the limit is bounded by the lim inf of this sequence. So we have, from this convergence, we can deduce by a previous theorem 2 facts. The first one is that this sequence, the norms of this sequence, it's bounded, which means that there exists a constant Cx, which is finite, such that m and x, it's bounded by this constant C for all n. And second is that the limiting point, which is called ax, the norm of this limiting point, it's bounded by the limit inf of the norms of m and x. So we proved these 2 facts in a previous lecture. So here we can repeat the first part of the proof. We have that for each x, the norms, it's uniformly bounded. By introducing a sub-additive positive homogeneous continuous function, we proved that these bounds entail that actually there exists a finite constant C0 such that m and x, it's bounded by C0, the norm of x, and this for all n larger than 1, and for all x in x. Right, so we proved in the previous, in the proof of the previous lemma, we showed that it follows from this bound that there exists a finite constant C0 such that the norm of m and x is bounded by C0 times the norm of x for all n and for all x. From this bound and from this second bound, we deduce that ax, the norm of ax, it's bounded by C0 times the norm of x. And this proves that, and this holds for all x in x, so this proves that A, it's a bounded operator, which was my second claim. So up to now we proved that if we define ax as the weak limit of the sequence m and x, A, it's a bounded linear operator, so A, it's an element of Lxy. It remains to show that Mn converge weakly to A, but by definition, Mn converging weakly to A means that for all x, M and x converge weakly to A of x, but this we know already. We know already that for all x, M and x converge weakly to A of x. And so this completes the proof, as we've shown that there exists indeed a bounded linear operator, which we represented by A, and that Mn is converging weakly to A. So let me prove the following lemma. Let me assume that the space X is reflexive. And let's assume that the sequence, that we have a sequence Mn, and this sequence Mn is converging weakly to M. So Mn and M are elements of Lxy, and I'm assuming that X is reflexive. What I claim is that this implies that Mn prime is converging weakly to M. So here note, I'm assuming that the sequence Mn is converging weakly to M, and I claim that the sequence Mn prime is converging weakly to M prime. So here's the proof. So Mn is converging weakly to M. So this means that for all x, Mnx, it's converging weakly to Mx. Well, but what means that Mnx converge weakly to Mx? So these are elements of Y. This means that for all L in Y prime, MnxL, so remember in my notation, this means that this is L applied to the point Mnx, that this is converging to MxL for all Y in Y prime. By definition of Mn prime, this is X Mn prime L. Now we have here a bounded linear functional defined on X. So this is an element of X prime, and this is applied to X. And this is converging to X M prime L. So we know from the assumptions that for all X in X and for all L in Y prime, we have this convergence. So, because, well, this expression is equal to that one. So I will erase everything, just keep this information and complete the proof of the lemma. So I wrote here what we proved. Up to now, we proved that for any X in X, any L in Y prime, X Mn prime L converge to X M prime L. Where here again, X is a point in X. These are elements of X prime, so this is the value at X of this bounded linear functional. Now let's see what we want to prove. We want to prove that Mn prime converge to M prime. So Mn prime and M prime are bounded linear operators from Y prime to X prime. So remember, M prime, it's an element from Y prime to X prime. So to prove that Mn prime converge weakly to M prime, we have to show that for all L in Y prime, Mn prime L converge to M prime L. Weakly, sorry. But to prove that so these are now elements of X prime. So to prove that this sequence of elements in X prime converge weakly to this sequence of elements in X prime, we have to show that for all L in X double prime, Mn prime L, so the application of this bounded linear functional to this element, converge to M prime L. And it is at this point that I will use the fact that X is reflexive. Saying that X is reflexive is to say that all elements in X double prime can be represented by elements of X. So this means that if L is an element of X double prime, then there exists a Z in X such that L is equal to LZ. And what is the operator LZ? Well, it's the one such that M LZ for m in x prime, so that this is equal to m applied to z. So actually this is equal to zm. Right? To say that x double prime, it's reflexive, is to say that any element in x double prime is represented as an element of x in the following way. So L is equal to LZ, in which sense that, well, these are two operators in x double prime. So let me tell you how they act in an element of x prime. Well, LZ applied to m is m applied to z. And so, since L is reflexive, there exists a z such that L is equal to LZ. So this is saying that, so I'll just replace, so this is what we need to prove, but now I'm using the fact, right? So let me recall what we are trying to prove. We are trying to prove that mn prime converge to m prime. To prove that mn prime converge to m prime, we have to show that for all L in y prime, mn prime L converge weakly to m prime L. But to prove that, we have to show that for all L in x double prime, we have this convergence. But now, we use the fact that L is actually equal to some LZ. And so, applying this identity to this line, what we get is that since L is equal to LZ, what we need to prove is that this holds. What we have to show is actually that mn prime L, LZ, converge to m prime L, LZ. Right? We have to show that this holds for all L in x double prime, but all L in x double prime are represented by some LZ. So actually what we really have to prove is that this convergence holds for all z in x and all L in y prime. But by definition of LZ, this expression is z mn prime L. And this one is z m prime L. So what we need to prove is that this convergence holds for all z in x and for all L in y prime. But this is exactly what we proved. We proved that for all x in x and for all L in y prime, we have this convergence, and this is exactly what is written here. This is exactly what we need to prove. So this completes the proof of the lemma. So we just proved that if the space X is reflexive and if we have a sequence Mn converging weakly to M, then Mn prime is converging weakly to M prime. Let me show that this statement is false if we replace weak convergence by strong convergence. So let me give you an example in which we have a sequence Mn converging strongly to M, but Mn prime does not converge strongly to M prime. So the example is to take X, the space L2. So this, remember, is the space of all sequences Aj, where Aj are, say, real numbers, and we have that the sum of the squares is finite. So this is the space. We know that this is a Hilbert space, and the norm of A, of a sequence A, is equal, if we take the square of the norm, this is Aj squared. So this example appeared many, many times, so I won't give you more details about that. Let me just define the operator Mn. So Mn will be an operator from X to X, so from L2 to L2, and it takes a sequence Aj, and it sends this sequence to the sequence in which the first coordinate is An, the second one is 0, and so on. So it's clear that, well, this element, it's an element in X. So Mn, it's a map from X to X. It is, of course, linear, and it's also bounded because it's, well, the norm of Mn, it's bounded by 1. I leave it to you to check that the norm of Mn, it's bounded uniformly by 1. And what I claim is that Mn converge strongly to the operator which is 0. And to show that Mn converges strongly to 0, what I have to show is that for all x in L2, Mnx converge to M applied to x, but this is 0. And let's prove that. So let's compute the norm of Mnx and square. So this is Mn applied to a sequence x is the sequence xn 0, 0, 0. So this is the norm of the sequence xn 0, 0, 0, the norm square. And, well, by definition, this is xn square. And this, of course, converges to 0 because the sequence x belongs to x. So the square is summable, and if the square is summable, which means that the intervals xj squared converge to 0, so xn squared is converging to 0. So indeed, we proved that Mn converge strongly to 0, and now I claim that it's not true that Mn prime converge strongly to 0. So I'm giving you an example of a space which is reflexive and in which we have a sequence Mn which is converged strongly to some m, in our case 0, and Mn prime does not converge strongly to 0. By the way, I didn't said it before, but L2, we have seen already that L2 is reflexive. So now let me compute Mn prime. By definition, Mn prime is such that Mnx, so L, this is equal to x Mn prime L. So I want to compute Mn prime, and the way in which I can compute Mn prime, it's through this identity, which holds for all x in x and for all L in y prime. But, well, now y is equal to x, so L belongs to x prime. And we know that x, it's a Hilbert space. So actually, L, we can identify x prime with x. And this identity becomes the scalar product of Mnx with a point y in x. And this is equal to x Mn star y. So this is the way in which we define the adjoint. So in the Hilbert space, the transpose becomes the adjoint, and the definition of the adjoint, it's given by this formula. So now this is true for all x in x and y in x, and this formula allows us to compute Mn star. So this is true for all x and n, so this is the, by definition, Mnx, it's the sequence which starts with xn and it's 0, and this is y. And the scalar product between a sequence y and this sequence, well, this is equal to xn y1. So the left-hand side, it's equal to xn y1. So now let's compute the right-hand side. The right-hand side is, so this is, let me call that z. Mn star sends x to x. So let me call this new sequence Z. And so this is just the scalar product between x and z. So this is the sum for k larger than 1 of xk, zk. And this has to be true for all x, all sequence x. So from this fact, we get that zk has to be equal, for this identity to hold, we have that Zn has to be equal to y1, and Zk has to be equal to 0 for k different from n. Right? If we want this identity to hold for all x, we get immediately that zk has to be equal to 0 for k different from n, and for k equal to n, we have xn, so zn has to be equal to y1. So this is, so mn, so we have now a formula for mn y. This is a new sequence, and this sequence is 0 everywhere, but on the coordinate n, it's y1. So this is equal to 0, 0, then y1, and this is at the nth position, 0, 0, and so on. So I will erase everything and keep just this formula. So I erased everything and just kept the formula for mn prime or mn star, since we are in a Hilbert space. Mn star of y, it's given by this sequence in which we have zeros everywhere, but on the nth position in which we have y1. Now I claim that mn star does not converge strongly to 0. And, well, this is clear because if you take y in x, the norm of mn star y square, that this is equal, well, to the square of the norm of this element, and this is y1 square. And so it's not true that mn star y converge to 0, because if you take a sequence y such that y1 is different from 0, mn star y does not converge to 0 because its norm does not converge to 0. Its norm, it's a constant equal to y1 square. So mn star does not converge to 0, and we have an example in which we have a sequence of bounded linear operators which are converging strongly to 0, but their dual is not converging strongly to 0. So the lemma is false if we replace weak convergence by strong convergence. So let me complete this lecture with a theorem. So assume that we have a sequence Mn in Lxy, which satisfy two properties. First, that it's bounded. So there exists a finite constant C0 such that the norm of Mn is bounded by C0 for all n larger than 1. And let's assume that there exists a dense subset of X such that Mnx converge strongly for all x in D. So I'm assuming that the sequence is bounded and that there exists a dense subset of X which has the following property: Mnx converge, so for all x in D. So for all x in D, there exists a point in Y, call it Ax, such that Mnx converge to Ax for these points. Now, what I claim is that this implies that actually Mn converge strongly. And what does it mean that it converges strongly? It means that for all x in X, M and X converge strongly. And we have seen that if for all x in X, M and X converge strongly, actually this implies that there exists M in Lxy such that Mn converge strongly to M. So the theorem reads as follows. Assume that you have a sequence of bounded linear operators which is bounded and for which there exists a dense subset of X such that the sequence M and X converge strongly for all X in D. Then I claim that Mn converge strongly, which means that there exists a bounded linear operator such that Mn converge strongly to M. So I just kept the hypothesis of the theorem. We have a bounded sequence, it converges in a dense subset. And let's prove the theorem, which is very simple, but as you'll see, very useful. So to prove that Mn converge strongly to M, so to prove that there exists M such that Mn converge strongly to M, we have seen earlier in this lecture that it's enough to show that for all x in X, M and X converge strongly. Right? Because, well, if for all x, M and X converge strongly, we are able to construct bounded linear operator for which M and X converge to Mx for all x in X. So it's enough to prove that for all x, M and X converge. We know that for all x in a dense subset, we need to extend this property to the whole set. But to prove that this sequence converge, it's enough to show that it's Cauchy. Because Y, by assumption, it's a Banach space, so it's complete. So it's enough to show that this sequence is Cauchy. And so let's prove that it's Cauchy. To prove that it's Cauchy, we fix an epsilon positive. And we have to show that this sequence difference between two terms, it's very small if the coefficients are large, and it's large. Well, so fix that epsilon. We know that D is dense. So we know there exists Y in D such that the distance from X to Y is bounded by epsilon. Now, what we need to estimate is M and X minus Mx. We need to show that this sequence is Cauchy, so we need to estimate the norm of this difference. We use the triangle inequality to insert Y in this term, so this will be bounded by Mnx minus Mny plus Mny minus My plus My minus Mx. So we just inserted Y in our expression, and now we will use the fact that the sequence Mn is uniformly bounded to estimate the first term. So the first term by linearity is Mn applied to x minus y. We have seen that this is bounded by the norm of Mn times the norm of x minus y. And we can proceed in the same way for the last term, which is bounded by the norm of mm times the norm of x minus y. Now, the norm of Mn and the norm of Mm are bounded by C0, and x minus y, the norm of x minus y is bounded by epsilon, so these two terms are bounded by 2 times epsilon times C0. Fine, but now x disappeared from our estimate. It remains this last term, but y, it's an element of D. So we know that M and y, it's converging. Since it's converging, it's Cauchy. So which means that given that epsilon, we can find n0 such that if n and m are larger than n0, this difference is bounded by epsilon. So this means that this expression it's bounded by 2 times C0 plus 1 times epsilon for all provided n and m are larger than n0. And this proves that this sequence is Cauchy and therefore that it converges. And this is what we needed to prove.